Hello, this is Mr. Linares, going to go over the 4 electrical faults. This has been talked about in lab already, and you should have seen it a little bit through Electude and what have you. However, sometimes having just a plain boilerplate explanation of things might help out, okay? So what I have here is I'm going to be putting some slides or pictures up here that were made with the whiteboard here. So sometimes it may look a little weird, but it should work fine. And as I talk through these things, I will be posting these pictures in Canvas for you. Okay, everything that you have right here along with this video is going to be provided to you as a resource, and it's a non-negotiable studying things you got to get done for the sake of you getting a good handle on how electrical systems work. Okay, we've done Ohm's law, we've done some of the basic circuit types, series and parallel, and we're looking at the faults now. Okay, and along with this, we will be dealing with series parallel circuits here soon. But I want to just get into some of the more critical aspects of things and get them, and then start fleshing out more of the details of what we've already covered as the semester goes on. That way, just in case something happens, you have the core knowledge that you need. Okay, so I'm just trying to play it safe here, as well as keep things varying, so you don't get stuck in a rut. You know what I mean? All right, so here we go. We're going to talk about the 4 faults. Now, when it comes to the 4 faults in electrical, okay, we have the 4 faults. Some teachers, some schools of thought say 3 faults. I will explain this as we go on and why I say 4. Okay, we have open circuits, which is a break in the circuit where no current can flow. We have unwanted, where some people may say high resistance. Which is, corrosion or loose connection in the circuit, sometimes even a wrong component maybe being put in. It's slowing down the current flow, causing poor operation of the circuit. Now, the reason I use the term unwanted instead of high is there are some components in the vehicle which would register a high resistance value, just like to your eyes. This is, wow, looks like a high resistance value, and I don't want you to get that confused. So I say unwanted resistance. Most people will, say, hey, it's got high resistance in the circuit, with everyone understanding that it's unwanted. For right now, since we're just beginning, we'll use these terms together, okay? Then we have shorts, okay? Now you have a short to ground, which is an unwanted pathway to ground. Typically, it's before a load, okay? If it's after a load, it usually doesn't get noticed. Still can cause problems, but typically doesn't get noticed right away like a short to ground would be. This is because if you have a shorted connection to ground, that means like a hot wire is touching ground before a load, current's going to flow too quick because of the low resistance connection, melts the fuse open, then the circuit fails. That being said, if you had a wire that's contacting ground after the light, it just acts as another ground. Okay, and the only problem you run into is like more of a long-term problem with wire integrity and corrosion and things like that, which can present other problems. For right now, we're just going one fault for one reason at one time, so we will stick with the before load for right now. Okay, understand that most of these things do have more to it. This is just going to get you the starting information you need to get begin wrenching and what have you. The next short is called a short to power. Okay, and you get your short to power. That's an unwanted pathway between 2 circuits. You turn a left light on and a right light comes on. You turn on the map light, and then your compass goes dim instead. It activates that. You turn on, maybe you tap your brake lights and your horn goes off. Okay, I mean, some of these are exaggerated, mind you, but basically the wrong component's working when you activate a circuit. Now it means two hot wires have managed to touch, and the current is going to flow to the wrong circuit. It doesn't stop the original circuit from working. It's just both would be working when they shouldn't be. Okay, and now we're going to be explaining all of these. Now the reason I say four faults instead of 3 is because these two are classified as shorts, unwanted pathways for current flow, but they behave differently, quite wildly. Okay, so I put the division in there to help keep everything organized in your head. Okay, so let's get on with these 4 faults. Clear up the board here, and let's go ahead and get to doing a little explaining, shall we? So I'll go ahead and put this over here. Okay. Now here we have an open circuit. An open circuit is a break or a cut in the circuit where no current flows. An open circuit is voltage applied up to that open. Voltage is always available up to an open, provided you have the circuit on, of course. Okay, provided your intention is to have the circuit on. Opens are located between the last place good voltage was found and the first place it reads 0 volts. Okay, that is to say, if I have a break in my circuit before my light here and the light is out, it is not even working at all, completely out, I would get my meter and I would trace it. 12 volts here, 12 volt fuse, 12 volts at the switch, go to the connection before the lights parallel off and say, oh wow, I have 12 volts here, that's marvelous. I go over between there and the bulb and I see 0. Uh-oh, I have a problem. I have 0 volts at my bulb, so I know that I've got a problem here because 12 volts back here and 0 volts over here. That means the open is right in between somewhere. Now in a little diagram, little sketch diagram like this, it's really easy to see. It's nice and convenient. It's tiny. You know, you can just see right in front of you everything all you want. When you get to a real car, okay, that little representation here that I have, this could be 6, 7, 8 feet of wire that you're dealing with. Okay, for right now, we just got to get the concept down because the physical part of finding things isn't bad at all once you understand what the diagnostic and theory part of it is. All right. So again, it's a break or a cut in a circuit. No current can flow through there. Voltage is available up to my open, like this 12 volt reading I have right here. Opens are between the last place good voltage was found, right here, and the first place that it was lost, which is right here. Okay, that's where my open's going to be. It's characterized quite simply by it doesn't work. Okay, the circuit doesn't work. You turn on the light, the fan, the motor, whatever you have, and it just doesn't function. Okay, the knee-jerk response you should have is open circuit somewhere, somehow open circuit. All right, so that takes care of opens. We will be dealing with this in a diagram setting in the next video. We'll take this and actually apply it to a real diagram. Okay, let me get rid of this. Go ahead and go find the high resistance one, the unwanted resistance. Put this over here. There we go. Unwanted or high resistance. If this looks familiar, it was where it works very closely to how an open works. Okay. We must remember when dealing with a resistance concern that resistance consumes voltage. Resistance is going to use up voltage. So if it happens where I don't want it, it's going to rob the rest of the circuit. Okay. Unwanted resistance or high resistance is between the last place you had good voltage, and I put that in quotes, okay, your good voltage reading that you want, and the first place you had weak voltage, not no voltage, weak voltage. Now keep in mind, even if you have a reading that's millivolts, okay, that's weak voltage. 0 is 0. Millivolts would still be something, okay, depending on you know, how severe the resistance is. Sometimes the resistance can be so high and take up so much voltage that it behaves like an open, okay, because the light wouldn't work, okay. However, the difference is there's still some current flow through there because there's still some kind of connection, all right. So high resistance has some kind of connection, and open is no connection, okay. So high resistance can be caused by wire chafing, corrosion, loose connection, or partial wire cuts. Okay, then the difference between a partial wire cut and chafing would be one was a tool on accident or something, and chafing is when wires rub up against metal like this. Okay, just to give a little bit of a illustration here. Say we have a wire, that's our wire sheath on the outside, the plastic coating on the outside of the wire. And then in that wire, okay, we have our conductors, okay, all the little strands going back and forth, right, in there. And what could happen is if the wire chafes, it could score away a chunk of this wire here, causing a lack of connection and only leaving a few little strands here. That's going to limit current flow through the wire. Let me clear this up. Likewise, I may have corrosion, and that's the wire gets exposed to the elements somehow somewhere else down the line, you know, or add a connection or something like that, and corrosion builds up in there, causing current flow to slow down, okay, because it's adding resistance. Corrosion isn't very conductive, so you're going to end up limiting your current flow through there. Again, it's not no connection, it's slow connection at that point. Now, we could also say partial cuts. Okay, so maybe it's something very sharp that has come there. It came across a blade or a tool or something, and it partially cut open, okay? There's still a little bit of wire left in there to help flow, but it's still not the best it's supposed to be. Usually that's some kind of human error. Now, you also have poor connections. Now, let me erase this. Got to make a little point here. What happens is when we have electrical connectors, we got a terminal, okay, and maybe it is square or round or what have you, okay, it doesn't matter which shape, it's usually one or the other. And what will happen is I have a terminal that's going to go in there, it's going to slip inside the terminal and connect, and I want that connection to be as good as possible all through here. However, if this connection is loose or poorly fitting, where it's like this and there's all this room in here, okay, where it can jiggle around, I'm not going to get the best connection I can, and it's going to limit current flow, okay, causing resistance. Okay, the the high resistance fault is characterized by the circuit works poorly. That's a slow fan, that's a dim light, that is a motor not turning as best it can, a slow wiper blade, all right, anything that's working weakly, okay, or poorly. Now, how we find it, okay, we talked about that the last place I had good voltage, okay, between there and the next place that I have weak voltage is where I'm going to have my resistance, very much like the open circuit. I have good voltage here after tracing it down, and then have bad voltage here, okay, not none, just bad or weak or poor. Pick your negative term there, right? So if I have good voltage here and not good voltage here, in between I have some kind of unwanted resistance. This is where diagramming comes in handy when you learn how to read diagrams, because you may end up going to a component saying, hey, I don't have the right voltage. There might be something before it that's supposed to be taking it from it, and there might be some other problem being caused. So you're going to have to be able to read the whole diagram to get a handle on that, okay? All right, so that is high resistance for right now. Let's go ahead and clear the board. These are going to get progressive here. Okay, talking about shorts to ground. Here we go. Shorts to ground. Now, when we're talking about shorts to ground, we're talking about an unwinded pathway to ground, typically before a load. That's where we noticed most often. Okay. The reason a short to ground will be noticed before a load most often is because if it happens before a load, high current flow will happen due to very, very low resistance, and then the fuse will get melted open. If it happens after a load, the voltage has been consumed, the current has already been resisted, and then that will go ahead and just act as another ground. You may not notice it for quite some time, and depending on how the severity of the short to ground, it may may invite corrosion because of a cut wire or something like that, and then you notice it because of a resistive effect it started to build up rather than an excessive current flow issue. Okay, so as far as the fault itself goes, we're going to concentrate on it being before the load because that is the most problematic you're going to run into. Okay, now short to ground is a low resistance contact between a hot wire and ground before loads, causing high current flow, which melts the related fuse open. Now, people will say it blew a fuse, people will say the fuse popped, and they're talking about the fuse melting open from the high current flow. They do make a little bit of a snap or a pop sound, and when it does that, that's where the term comes from. It popped, it blew a fuse, okay? Older fuses, glass fuses, house fuses from way back, they would make a distinct pop sound, the pow, and the circuit would fail because of that unwanted contact to ground or an overload in the circuit or what have you. Now, please keep in mind, our fuses now are very, very tiny, very hard to hear, okay? And keeping the term melt open, okay, is going to help you a lot better because you're going to understand that high current flow is causing it to melt open. That leads you in the right pathway for the diagnostic. Okay, shorts to ground are caused by chafes or human error. You might have a wire chafing against a part of the engine or frame or something like that, and it rubs itself open. But rubs itself to ground. Now, what will happen is typically that's a bracket missing, a clip failed, something that was holding the wiring harness in place has let go or failed, or somebody didn't put it back in repair. Okay, or somebody has been modding the car and didn't put it back or replace it, or what have you. Sometimes there's an accident that happens and the body shop puts the wires in the right location but doesn't put the appropriate clips and restrainers that keep the wiring harness from moving and rubbing all over the place. That's not terribly uncommon, unfortunately. Okay, so it's usually some level of human error at someplace. Even when it happens as part of a factory warranty, typically it's poor design or somebody routed a wire in the wrong direction during construction of the vehicle. And again, human error, right? Now it's characterized, short to ground is characterized by the phrase, it blew a fuse. We understand what that means, okay? And I leave it at that simply because it puts you in the right frame of mind to get ready to think about it. It blew a fuse. Okay, so let's play with this here a little bit. You have got right here an unwanted connection to ground before the load, okay? This connection before the load would only become a problem once your switch is connected, okay? So if you connect the switch, you push down on the brake switch and you make your connection, current's going to flow. Ideally, the lights would light up, consume the voltage, and everything would be done. But instead, we've got this connection to ground here. Now, this connection to ground is going to be a very, very, very low resistance connection. And if my resistance is really, really low, my current is going to go really, really high. Okay? That high current flow is going to be going through the circuit for usually just a very brief moment, causing the fuse to melt open because of the high heat. This fuse, being a circuit protector, is designed to melt open before the level of heat that opens it affects the circuit in general. Okay, so this is actually what the fuse is for. It's to protect the circuit from high current flow. Okay, that's why it blew a fuse is the big tell for this kind of fault. Now, when you go looking for it, you may use an ohm meter to track the thing down. Okay, now what you have to do here with the ohm meter is first you got to make sure that your fuse is not in here, because let's block this out real quick. The fuse will be pulled out. It will likely still be blown open, so you don't have to worry about that. But on the ground side of the fuse, on the circuit side of the fuse, okay, you're going to go ahead and connect your meter right there. And then what you'll do is you're going to probe in various places, preferably places with connectors and things like that in the circuit. And as you do that, okay, right here with the switch closed, okay, if you probed here, you would notice nothing. If you probed here, you would notice nothing. It would still read open circuit, OL, on the meter, okay? So you have nothing here and nothing here at the switch, okay? Leaving this switch open, however, leave the switch open. You come on over here, and then all of a sudden, maybe you see an ohms reading, 0.1 ohms, 0.2 ohms, low resistance contact. Uh-oh, I have got a bit of a problem here. Okay, so I know that I'm on the right path. So I can go ahead and get rid of the idea that it's over here or over here. Right, so I'm still tracking this thing. Now, let me clean this up a little bit so it's easier on your eyes. Get rid of this too while I'm at it. So I know that it's somewhere on this side of the switch, okay? I'm definitely positive this. So what I'm going to go over here and do, again, I understand this is a short to ground and that the lights did not light up and it melted a fuse open. So I'm going to feel confident about coming here to my light connector, disconnect my light connector. Then I'm going to go ahead and probe again. So, well, I still have got that connection to ground over here. Okay, now what I've done is I've isolated my short to ground physically in this circuit right here, this portion of it. That limits where I'm looking in the car. Okay, I may not be in the dash anymore. I'm not over here by the brake pedal anymore. This section of the wire might be out along the frame somewhere. Okay, you know, since I disconnected this connector, I know it's not in the trunk wiring or anything like that. There's a bunch of possibilities here. It's a simple isolation technique. All right, and that's just a very brief beginner's example that we will be able to work with. Okay, let's go ahead and get on to short to power. Okay, when it comes to shorts to power, unwanted pathway for current flow between two circuits. Again, unwanted pathway for current flow between circuits. It doesn't have to be two, it could be more, but typically, you know, it's two. For our purposes, we'll stick to two, that way it's easy to understand here, okay? It's caused by wires chafing together, being pinched together, or human error of some kind. Just like the short to ground, more often than not, there's some level of human error involved in this sort of thing, okay? Not too many spontaneous shorts to power happening, okay? It's not like the elements got to it with a high resistance issue or something like that, or you know, something, some simple, you know, catastrophic event of some kind. Typically, there's some level of human error involved in this. It's characterized by erroneous operation of the circuit when another circuit that's unrelated is activated, okay? So if you look at our diagram here that we have, you'll see that you have the boo switch here, the brake on off, BOO switch, brake on off, boo switch. And over here you have brake lamps. My fuse, my battery, everything that I need for the circuit. So I go ahead and I activate my brake lamps And then my brake lamps are supposed to come on and everything's supposed to be fine. Except in this diagram, if I push down on the brake switch, okay, the brake pedal, right? I'm going to, through this unwanted connection, activate my horn. So I turn on my brakes, okay, by pushing on the brake pedal, but then I hear the horn honk, okay? And it may not even be a full connection or anything, but it's still gonna make some noise, right? So it ends up honking. And I know that's crazy. It's not supposed to be happening, all right? You know, or the other way around. Maybe it's nighttime, which is pretty much when you only notice it. And for whatever reason, say you go stop off and you know, you're going to go pick up an order of food online and you're taking forever to get out and you get impatient, you honk your horn, okay? You're not supposed to, but you do. You just, I'm hungry, I want to honk my horn to get their attention, to get my food. And you end up honking the horn and you see in the mirror, okay, against a wall or another car or something, the glow of the red brake lights going. So, wait, beep, beep, and you see the lights. It'd be a bit of an issue, okay? That's to tell that you've got some kind of short to power. Two circuits that are activated together when they shouldn't be. Okay, and again, if this is happening on the power side, it's going to be noticed more so than the ground side. Okay, it's like if you had two grounds shorted together after two circuits, nobody's going to notice. Okay, so here we go. Unwanted pathway for current flow between two circuits is caused by wires being chafed together, pinched together, or otherwise human error. Its erroneous circuit operation is occurring when an unrelated circuit is activated. It's characterized by the wrong circuit working. Okay, so now when we go to try to find this, okay, a simple way to start tracking it down is we go ahead and we find our ohmmeter. Okay, we go ahead and get that. And I know that when I turn this on, the horn comes on. If I turn this one, the lights come on, and vice versa, right? Well, now I need to find these things. So what I'm going to go ahead and do is I'm going to remove my fuses, okay, because if I'm using an ohmmeter, I do not want any kind of power applied to this circuit, okay? So now, at this point, since there is no power applied to the circuit, and I'm not looking for a specific resistance value, okay? Oh, I just realized something. Sorry about that. I've got to fix that for the picture that I gave you guys. Okay. Since I'm not looking for a specific resistance value or measuring a part for some diagnostic purpose, and I'm only using the meter just to kind of give me a hint about where I'm going to find the problem physically, I'm not terribly worried about components being connected at this point. Okay. Usually when you're using an ohmmeter, you're going to have everything very isolated with the meter itself out of the circuit, so you can get a good measurement for a resistance reading. Right now, we're just looking for any kind of connection right now at all. So what I will do is, again, I have my fuses out. These switches are open, okay? And what I would do, just to cover all the bases, I would go ahead and I would go here and then here and see if I have a connection. Okay, right there. And in this scenario, I would read L out of limits open. Some meters will give you the number 1 on the far left. Okay. We're going to use OL for open here. So let's say I didn't find anything there. Then nothing between these two circuits. Okay, the switches are open, these fuses are out. I made a ohmmeter connection between these two by using the terminals at the fuses, didn't find anything. That eliminates everything up to these switches. Okay. Now what I'm going to come on over here and do is I'm going to connect, oops, I'm not going to erase my work is what I'm going to do. Okay. I'm going to go ahead and connect 1 meter lead here to this side of the switch terminal. And then I'm going to connect one over here. And then all of a sudden, I should get some kind of reading. Maybe it says 0.2 ohms or you know, 0.33 ohms or something like that. However potent the connection is, right? It's enough to travel current between the two circuits. So I have that. Well, now I need to isolate this, okay? Because I know it's on this side of the switches for sure, okay? So what I'm going to do, I'm going to go ahead and erase these again. Hopefully not the meter again. I'm going to go ahead and I'm going to disconnect at my lights. I'm going to disconnect at my horn. And then I'm going to go ahead with my meter. Okay, I'll come over here and I'll get a reading. And let's say I get that reading, you know, 0.2 ohms, 0.3 ohms, whatever it might be. It could say 6 ohms if you want it. There's a connection there. That's our problem. Okay, we're just looking for a connection at this point, right? So then what happens is I end up isolating that. Now I know, without any doubt, that between my switch right here, okay, and my connections right here, that I have got that short to power. That's where I'm going to start looking. That's where physically I'm going to be going through things. In this scenario here with our brake and our horn, we might have a scenario where we have our steering wheel, okay? You have your steering column that's going to come off of this. And my horn wiring lives in the steering column, right? Okay, right here in the steering wheel. I might have my, oops, I'm starting to make bad words here. Okay, horn. And then down here, I have my brake pedal. But the wiring, way up in here, okay, my conduit for my wiring on my wiring harness, I might have a wire that comes down here to my brake switch and more wires that go up here to my horn. Okay, so I know that physically in the real world, my space that I'm looking for, I'm not going to worry about the steering column because there's no brake light up here in the steering column. Likewise, I'm not going to be looking for the horn wire down here on the brakes all by itself. But in this center trunk of the wires where everything comes together, in this area right here where those wires may be together physically, where they start routing together, that's where I'm going to start looking, okay? And maybe there was an alarm person in there that was installing an alarm and he accidentally pitched a couple of wires together when he was looking for the right thing to do, okay? There's a bunch of possibilities for this sort of thing, and you could spend all day speculating if you want, okay? But these are just some little ideas to get you started, all right? So to clear this up, I will fix this, actually, yeah, I'll fix this before I post it to the, for you, all right? So those are the basics on the 4 faults. The, you know, little cheater notes. I highly advise that you would copy these pictures into your phone or your computer. Keep them handy. They are also very good to write on 3x5 cards or a sheet of paper to keep with you. This is the sort of thing that are just little helpful tips, okay? And then the day is going to come where you don't need to worry about them anymore, okay? Because you have that understanding solid, and then maybe pass these along to somebody that could use them, okay? So that is that. I hope you all have a good day, and this video shall post here tonight sometime. And well, tonight it's the 16th of September. Sorry. Okay, and it won't be too much longer before it posts. All right, and I hope you have a good time. If you need any help, you get a hold of me. Take it easy. Bye bye.